So by now, for number 9, we know we need to find our derivative. We need to find y prime, and y prime is equal to negative 4x cubed plus 36x. And let's also, while we're at it, find y double prime, and that's negative 12x squared plus 36. Okay, we'll set our y prime equal to 0. Y prime equal to 0 when negative 4x cubed plus 36x is equal to 0. Okay, and if we factor out a negative 4x, then we're going to get x squared. Be careful here, minus 9 is equal to 0. So our three critical points are x. Maybe I should do this first. Let me keep factoring that. Negative 4x times x plus 3 times x minus 3 is equal to 0. Let me just double check my math. I have y prime. I set y prime equal to 0. Factor out a negative 4x. And I get three critical points for this function. Again, it's a polynomial function, so we get x equals 0, x equals negative 3, and then also x is equal to positive 3. Those are the three numbers that will cause y prime to be equal to 0. So our y prime test, which we use to determine the sign of y prime on either side, on any side of these. Let me make a better sign chart here. Let's put negative 3 there, let's put 0 here, and let's put 3 there. Again, we know that the domain of this function is all real numbers. And to the left of negative 3, we're going to pick a test value, let's say, of negative 10. Okay, if we put in negative 10, our first factor, negative times a negative there. I'm going to keep the negative 4 in there. I could just multiply both sides by, or divide both sides by negative 4, but it's in there, it's okay. Negative 4 times negative 10, that's a positive. Negative 10 plus 3, that's a negative. And negative 10 minus 3 is also a negative. So we see on the interval from negative 3, or negative infinity to negative 3, the y prime is positive. Of course, we could have looked up here at this negative x to the fourth. We know, guys, that negative x to the fourth opens down. It might have 3 bumps, it might have just 2 bumps, but nevertheless it opens down. So initially it's going to be increasing anyway, so that confirms that part. So we should know our shape of our polynomial functions of different degrees. In between negative 3 and 0 we have a negative 1, let's say. First term would be positive, and then second term, negative 1 plus 3 is positive, and negative 1 minus 3 is negative. So on the interval from negative 3 to 0, we see that y prime is negative. Okay, and so in between 0 and 3, we can replace x with 1, let's say. Negative 4 times 1 is negative, 1 plus 3 is positive, 1 minus 3 is negative, and so on the interval from 0 to 3, f prime or y prime is positive. And then finally, to the right of 3, let's say 5. We have a negative 4 times 5, that's negative. 5 plus 3 is positive, 5 minus 3 is also positive. And so just confirming what we really already knew here is that y prime is negative on that interval. And then if we want to know the behavior of y would go up. So increasing, then decreasing, then increasing, then decreasing. And so we were going to be able to fill in our chart there nicely, and we might as well go ahead and do that. A is asking us for when is the function y increasing. So we can see that y is increasing on the interval from negative infinity all the way to negative 3. Okay, but also on the interval from 0 to 3. Okay. And then part B is asking us where the function y is decreasing, and we can see that y is decreasing when y prime is negative, and that would be from negative 3 to 0, and also on the interval from 3 to infinity. 3 to infinity. Okay. Well, C is asking us for concave up and concave down. Well, we don't know that yet, but oh, really we have to find our min and our max? What a bummer. At x, we can see we have a min. Let's do that first. We have a min value right here at x equals 0. Okay, that's not so bad. So at x equals 0, we have a minimum value. And what is that minimum value? Well, y of 0 is 11. Okay, we just replace x with 0 in our original equation for y. And then where would we have our max values? Well, we have our max values when x is equal to positive and negative 3. Okay, so here's where we had our min. Here's where we have our, what color should I use? Here's where we have our max, and we have our max over here. Notice that the x terms in, let me erase this here. Can I do that? Yeah. In our original function, our x terms are to the evened powers, and so whether we put negative 3 in or positive 3 in, we're still going to get the same value. So let's just put a, let's start with the left one. Let's put a negative 3 in, and we see that y of negative 3 is the opposite of negative 3 to the fourth. It's going to be negative 81, and then plus 18 times negative 3 squared, and then plus 11. So we have negative 81 plus 18 times 9, that's 162, plus 11. And negative 81 and 162, that's 81, and 81 plus 11 is 92. So we see that when x is equal to negative 3 and when x is equal to positive 3, we have a maximum value, a local maximum value of 92. And then again, that occurs at x equals plus or minus 3. Okay? So then, if we want to figure out the rest, the concave up and down and inflection points, we need to come up with the second derivative, and we already did that part, but set the second derivative equal to 0. So y double prime is equal to 0 when negative 12x squared plus 36 is equal to 0. Okay, so where's that going to happen? Well, that's when 12x squared is equal to 36. In other words, when x squared is equal to 36 divided by 12, which is 3. So when x is equal to plus or minus radical 3. Okay, so that's when y double prime is equal to 0, and we need to conduct our y double prime test, and we have negative radical 3 and positive radical 3. But keep in mind, we already know that the function f or y is concave down until the first critical point, or until the first inflection point, and then it's concave up till the second inflection point, and then we have concave down because we know the shape of polynomial functions. So I'll let you do the math on this. To the left of negative radical 3, we can see that f double prime is negative. In between the two f double prime critical points, we can see that f double prime is positive, and then and to the right of radical 3, we can see that f double prime is negative. So therefore, the shape of the function y would be concave down, then concave up, then concave down. Therefore, we can see our intervals on which f of x, or y in this case, concave up. So concave up on the interval from negative radical 3 to radical 3. And y is concave down. Part D, concave down on the interval from negative infinity to negative radical 3, as well as the interval from radical 3 to positive infinity, and therefore our inflection points would be at plus and minus radical 3. X equals plus or minus radical 3. I'm not really excited about finding our y values, but I guess we could. Might as well do that. Round out the problem. Y at negative radical 3 would be equal to negative the negative radical 3 to the fourth, and then plus 18 times negative radical 3 squared plus 11. And so what do we have here? We have negative, so radical 3 to the fourth is like 3 squared, so that's 9. And so we have negative 9 plus 18 times radical 3 squared, that's just 3, plus 11. So that's not so bad. 18 times 3 is 54. 54 and 11 is 65, and 65 minus 9 is 56. Okay, I get that right? 54 and 11 is 65. 65 minus 10 is 55, so minus 1. All right, so we have 56. So actually the coordinates then of the inflection points would be plus and minus radical 3 comma 56. All right, so that kind of rounds out that problem, and that is plenty of work there.